Please welcome Vojka Žunić, National Institute of Chemistry, Slovenia.
Good morning. My name is Vojka, and I'm leading the Knowledge Transfer Office at the National Institute of Chemistry in Slovenia. The core mission of our office is to transfer inventions and knowledge created at the Institute to the economy. We offer researchers with breakthrough ideas and an entrepreneurial spirit all the support needed to set up a company. One of such companies is also our nominee, ReCatalyst. The technology offered by ReCatalyst contributes to one of the long-term global challenges, that of creating a low-carbon society. We nominated the ReCatalyst to become the Falling Wall Venture Science Startup of the Year because they approached the setup of the company very systematically, from initial startup competitions to building presence and recognition in media. And now, in the fundraising phase, they can be seen as a case study for all Slovenian deep tech ventures. So if we talk about falling walls, they have really overcome many walls, both in terms of the scientific excellence and also building their venture. This is why they should become the Falling Wall Venture Science Startup of the Year. Good luck.
Breaking the wall of inefficient fuel cell catalysts. Matija Gatalo, ReCatalyst.
Hello, everybody. I started my journey to Berlin already 5 years ago when I attended the Falling Walls Lab in my home city of Ljubljana. So today, I'm finally here and able to present our idea in front of you. Did you know that in 2021, out of 90 million vehicles sold, about 3.5 million will be battery electric? Did you also know that in 2030, only in Europe, about 3.7 million vehicles sold will be powered by hydrogen fuel cell technologies? But currently, this is just a target. It's a target that we will not reach if we do not break the wall of the inefficient fuel cell catalysts. In order to completely decarbonize the transport sector, there is a tipping point where we start to increase the distance traveled as well as the vehicle weight, where battery technology becomes a much less viable option. And this is where fuel cell technology is going to bridge this gap. Fuel cells are a great technology also because on one side, they convert hydrogen as a fuel, and on the other side, oxygen from the air into clean electricity with water as the only byproduct. And the core that makes everything possible is the catalyst material. And currently, this catalyst material is made half, approximately, out of platinum. And shockingly, about half of this platinum is in current catalysts being completely wasted. So if we break the wall of the inefficient fuel cell catalysts, it is expected that by 2026, only the fuel cell catalyst market alone is going to reach 5 billion euros and over 30 billion euros by 2030. So actually, already today, we use platinum in our internal combustion engine vehicles in order to clean the exhausts. And on the other hand, fuel cells require currently significantly more. On one end, we have enough platinum to produce all of the internal combustion engine vehicles, but we don't have enough to produce or to reach the targets with fuel cell vehicles in 2030. Not in Europe, not anywhere. So the first solution that gets to my mind is maybe we can just get more platinum. So we could start mining asteroids, we could maybe explode a few stars, but we can do something that's much more sensible. We can just make the catalysts more efficient and use the platinum that we already have. Okay, slight problems with the presentation. Okay, so the main issue that the current fuel cell catalyst producers have is that they haven't yet found a way how to teach their platinum how to behave socially distant. They couldn't do it before the pandemic, and they still don't know how to do it today. So in their case, platinum sometimes likes to gather in larger groups, sometimes in smaller groups, and there's also places where platinum just doesn't want to gather at all. And with only 6 years of research and development and over 9,000 catalysts later, as well as one PhD, we have found a way at ReCatalyst how to teach our platinum how to practice social distancing. So let me show you how this looks in reality. So on the image, you on one side have a catalyst from one of our competitors, and on the other side, our own catalyst. And without knowing much else about the images, each black dot represents a platinum nanocrystal. And also what looks better to your eyes is going to perform much better in reality. So it seems that also platinum benefits from practicing social distancing. So we're actually quite young as a company, and we started by winning the EIT Jumpstarter competition towards the end of 2020. Shortly after, we officially incorporated as a company, as well as received the prestigious ERC Proof of Concept grant. We also entered, as well as completed, the phase 1 of the EIT Accelerator program, as well as finished the validation of our first generation MVP with both academia as well as industrial partners. We also applied for another European project under the program called the Pathfinder, and we're only now a few short weeks away from getting the results. We also signed an exclusive licensing deal with our nominating institution, as well as finished the development of our second generation MVP, and are now ready to scale our technology. So while we're quite young as a company, we're actually already on a journey for the last 2.5 years, trying to enable the hydrogen society. On this journey, we have made a lot of relations and partnerships across the value chain. We have received enough funding to kickstart our company, as well as many innovation awards for our technology. So we're now at the point where we're raising a seed round to scale this technology, and with that, I would like to thank you for your attention, and I'm ready for your questions.
Okay, questions? Yes, we have one here, please, in the front row.
You talked about, let's say, two main levers. One is increasing efficiency. I understood this with the pictures at least. And the second one is waste reduction. So how do you achieve waste reduction?
When waste reduction is basically by elimination of oversized particles. So currently, basically, the catalyst, what it does, it only works what's on the surface, so the platinum that's on the surface of these particles. So we are eliminating these oversized particles and really improving the homogeneity of the product. So we use less platinum, but gain the efficiency.
Yes, we have a... Oh, sorry, this question was first.
Is it going to be cheaper as well? So I understand you increase the surface, which means it's more efficient, so that's easy. But is it going to be cheaper?
I would say it's not easy, because if you would look at the catalysts... yeah, no problem. But if you would look at the catalysts like 6 years ago and today, you would see that the same problem still persists. So it's actually the uniqueness of our process that enables this increase in efficiency for the first time. And it's not only been... We saw that it's possible already 2 years ago, but we only really achieved this really significant breakthrough a couple of months ago. So it's really not a straightforward, solution. But could you just briefly repeat the question, about the... Yeah, so the cost, when we go to economies of scale, it shows that the main cost contributor is actually platinum. So everything else is very cheap, and also our process is water-based. We use very mild conditions. We use off-the-shelf reagents, so it's from all perspectives, it's us cost competitive as all others, but we're saving a lot of platinum.
Okay, the question here, please.
Well, thank you very much. I think beside efficiency and cost, the stability actually also plays an important role. Can you talk a little bit more about the stability of the catalyst during operations?
Yeah, so in terms of stability, we have an ERC project that's called 123 Stable, and our ERC proof of concept is called StableCat. So our main focus, besides the, let's say, ability to really reduce the platinum, is also to make the most stable catalysts when it comes to platinum. And actually, we're using platinum alloys. So we're already, in terms of also stability, we're already over the state of the art.
Okay, another question. I check online. No? Yes? No? Oh, here, sorry.
Great talk. What is a typical platinum particle size and the mean free distance?
Yeah, so that's maybe the neat part. In comparison to the commercial catalysts, we actually do not change the average particle size distribution, but we only eliminate the largest particles. So we're still talking about between 3 to 5 nanometer range.
We have a question here again at the first row. I know you have to run. Thank you so much, by the way, to the team here. Thank you.
Thank you. It's about growth. There's a big discussion about how quickly the H2 market will ramp up. Do you believe 2030, or what is your alternative if the path will be lower?
Yeah, I mean, with our solution, perhaps the fuel cell market can grow faster. But maybe we're not the only bottleneck. There's also the hydrogen supply and distribution, and also producing the hydrogen. So it's also on their end to provide the solutions.
Yes, last question. I hope it's a yes/no question. We have 20, 19, 18, 17.
Are there any other applications for your core technology of dispersion?
Yes, I mean, initially we could expand to the actually reducing the iridium in the hydrogen electrolysis basically markets, but we could also go to heterogeneous catalysis, so anything that requires distributing nanoparticles over conductive surfaces. So it's like what we patented is the platform technology, actually, but this is where we're currently putting all the efforts.
Okay, thank you very much for all these questions.